This is lesson 2 for chapter 2 in AP College Physics. Let's take a look at these three graphs on the left. Let's begin with graph C. In this particular graph, we have x, sometimes we might use the letter D for displacement. And what you can see here is that this displacement versus time graph, we have a slope that starts off rise over run. It's inclined a little bit, but this line right here is inclined a lot more. So what does the slope mean? Again, slope is rise over run, which is the change in y divided by the change in x. And in this case, my change in y is the change in displacement, and my change in x is the change in time. And of course, we know that the change in time divided by the change in distance divided by the change in time is velocity. So this is a graph of velocity. So the slope of my line is the velocity there, the velocity there, the velocity there, the velocity there. The velocity is getting greater and greater and greater because the tangent to the point along that curve is getting steeper and steeper and steeper. Now, if we were to do a graph of this information, and now that we have all these different slopes, we were to graph the slopes of these lines representing velocity versus time, we might get a straight line. And because we have a straight line, that means we have a constant acceleration. The acceleration is not getting bigger, the acceleration is not getting smaller. If we had started with a zero velocity, if v sub aught, v sub 0, happened to equal 0 meters per second, that means each time interval we increase by the same amount of speed. Let's say that our acceleration was 10 meters per second every second. That means after 1 second, we'd be traveling 10 meters per second. After 2 seconds, we're at 20 meters per second. After 3 seconds, we're at 30 meters per second, and so forth. We have a constant positive slope that does not vary, so we have a constant acceleration. So now, if we take this information and graph it up here, we can see that whatever that acceleration is, let's say it's 10 meters per second, that acceleration doesn't change. After this much time, we're accelerating at 10 meters per second every second. Same there, same there, same there, same there. We are continually increasing at 10 meters per second every single second, which of course at some point you can't continually maintain that. All right, the three kinematic equations that we use an awful lot in physics, first of all, is this one right here. If we think about acceleration as being velocity divided by time, and we multiply both sides by t, we get velocity equals acceleration times time, and this would be assuming that my initial velocity equals 0. If my initial velocity is 0, we basically get an equation that is a variation of the definition, there it is, the definition of acceleration. Now, through some simple algebra, and I have a handout on Canvas that you can look at to see how we take the equation right here, equation 2.6, and algebraically we end up with equation 2.9, that my distance, my delta x, if we're talking about moving in the x direction, is equal to my initial velocity times my time, which is basically the definition of velocity, plus, if we are accelerating, 1/2 acceleration time squared. So we have a couple of things here. We could say, for example, if my initial velocity is 0, this term goes to 0, and my distance equals 1/2 acceleration time squared. Or, if we wanted to, we could say what if my acceleration is 0? Then this whole term goes to 0, and then what's left is simply a variation of the definition of velocity. And then finally we have this equation, which can be derived algebraically as well. In this particular equation, you notice that we don't know what our displacement is. In the equation up here, we don't know what our final velocity is. Our final velocity is a mystery here. Here, our displacement is a mystery. When we come up to this equation right here, you can see that what our displacement is also a mystery. In any case, some books will write this equation this way. Some books will write the equation this way. The point being, again, if your initial velocity is 0, then v squared equals 2 acceleration change in displacement. What did I say? Oh, I'm sorry. I didn't mean to say, my mistake. I did not mean to say this displacement is 0. I meant to say that time is something we don't know. How long this took, I thought something was odd. Time is something we don't know in this equation. We can also say what happens if your acceleration is 0. Well, if your acceleration is 0, then we're basically saying your final velocity is the same as your initial velocity. So here are these three equations. You're going to see variations of these equations a lot in the first quarter. This is for straight line with a constant acceleration. I'll let you work through some of the math problems. We're just covering the basic content material. Let's, over here, by the way, there is a meaning to the area under the curve. The area under the curve is going to give you some function of the y-axis times the x-axis, some function of the two. Some function, in this case, of velocity times time. And that integral is another, in calculus we would call it the integral of finding the area under this curve from this point to, say, this point. That would be the total displacement. The total displacement when you have a constant velocity and then you accelerate and then you slow down a little bit and then so forth. Now, freely falling objects. Here the word free means under no other influences except gravity. So that automatically means we are disregarding air friction, which we won't disregard all the time. We'll do a lab where we have to take into consideration air friction. So when we talk about a freely falling object, and normally we can disregard air friction if indeed the object has a certain amount of mass, a certain amount of density, and air friction then becomes negligible. At least near the surface of the Earth, the acceleration due to gravity is constant. We typically, when we talk about gravity, round it off to 10 meters per second squared, which maybe you did in freshman physics all the time. Though in AP physics, we're going to pretty much exclusively use 9.80 meters per second squared, 3 sig digs, unless you were told something unusual, like you're deep down in a very, very deep valley like Death Valley or the Dead Sea, or more likely way up on top of a high mountain, where there is a variation to the acceleration due to gravity. It would be somewhere between 9.7 and 9.9. Though I doubt you'd reach either extreme most places on the Earth. Of course, if you're going now up into space, that acceleration due to gravity becomes less and less and less until eventually it fades to zero in places where, in a sense, all the gravitational pulls acting on you from all the objects that are very, very far away either cancel each other out or fade to almost zero, and then you are weightless because you have nothing pulling on your mass. In any case, you can see a video of somebody dropping a hammer and a feather, David Scott, on the moon, a classic video. Anytime an object is falling and we can disregard air friction, again, we say it is in free fall. And it's usually a good estimate to make. Now over here, a little reminder, when Galileo promoted the Copernican model, he was never really imprisoned. That again is an idea that came out of the Enlightenment and the historians in the Enlightenment, in which you felt like we are now enlightened because we have science and physics and we do not have to exist any longer under the shackles of religion, particularly the Roman Catholic Church. So they invented this idea of science against faith. And they used terms like imprisonment, totally false. And that history is now being fixed in the last 15 or 20 years. The Enlightenment, of course, came after the Dark Ages, and there were technically no such thing as the Dark Ages either. And I've been to Rome, and I've seen where Galileo would be. I saw a museum dedicated to him, and you could look across and see a place a villa where he stayed. Pretty nice digs. All right. Just a couple comments on this problem right here. When you do a problem like this, it's often a good idea to recognize that technically this problem has two parts. You could even say that this problem has three parts. Part one is going from there to the apex. And then at the apex, part two is going from there back to the starting point. Part one, part two, and then part three is from the starting point to where it hits the ground. You can also do this problem where you limit yourself to just two parts. The first part is going up and back to where you started from. And then all of the conditions that your kinematic equations give you for your velocity at this moment and your height at this moment, which is back to zero, and your velocity at this moment, which is the same as the velocity you started with, but going in the opposite direction, hence the negative sign. These are the values you plug into your kinematic equations to do the rest of the problem all the way down. But what you should notice is that whatever your velocity is here, let's get a different color for a while. Whatever your velocity is here will be here, but in the opposite direction. Whatever your velocity is here, your velocity will be the same, but in the opposite direction. Whatever your velocity is there, it'll be the same right there, but in the opposite direction. The other thing we should point out here is your velocity is zero in the vertical direction. In this vertical direction, or the y direction, your velocity is zero. The object for an instant has no vertical velocity at all. That is also true when you throw something and its projectile path looks like this. Its velocity in the vertical direction is zero right at the apex, not the velocity in the x direction. That velocity would be the same all the way across. We'll get more to that idea in the next chapter. The point I'm trying to make, of course, is here you have a mirror image. Going up and going down, they mirror each other. So when you have a problem where something changes, Whatever values you have at the end of the first part of the problem, you use them to do the second part of the problem. And that concludes chapter 2.